Okay. Okay, let's continue with the questions. Okay, so we did this question about second one, specific capacity and method of fusion and vaporization. Okay, let's try the third one. Okay, a block of copper of mass 0.5 kg. An initial temperature of 77 degrees Celsius. It's placed in a 0.4 kilogram of water. So block 77 degrees Celsius was placed in a beaker of water, which is 30 degrees Celsius. When thermal equilibrium is attained, the temperature of both copper and water is 35. After they place together, the temperature becomes 35 degrees Celsius. How much heat the copper block loses and how much heat the water absorbs. So what is the energy released by the copper? So the energy released by the copper, So of course what? MC theta, so M is how much? 0.5 C's of copper is how much? 400. And the temperature change is how much? 77, it dropped to 35. So give you the energy released by the copper. And do the same thing, energy absorbed by the water. So MC theta again. So 30 to 35. So what? M is M of water. So 0.4, C is C of water, 4,200. And the temperature change is how much? 30 become 35. So 35 minus 30. You get the energy. Joule. And comment your answer. First get the value first. Is it same or different? Yeah, same or different?
Same.
Same. So finally you got the same answer. So what is the comment? Comment? All the energy released by the copper has been absorbed by the water. No energy was released to the surrounding. Okay, all energy released by the copper is absorbed by the water. No energy released to the surrounding. Okay, so that's the comment. Okay. So let's move on. So specific latent heat, just now we discussed, okay, the same wording. The internal energy will come back later. During latent heat, kinetic energy does not rise, used to break progressively the bond between the molecules. There are no change in the average molecular kinetic energy, hence no change in temperature. Okay. So here, latent heat of must be supplied to change from solid to liquid, liquid to vapor, and solid to vapor. The specific rate of fusion is LF, and vaporization is LV. LV unit is how much? Joule per kilogram. Okay, it's joule per kilogram. You need to write this or an empty slot for you to fill up. So the change in state of M material, the energy required to given by. So what is the Lethonite energy formula? So the Q equals to MLF or MLV. Okay. So when the boiling, some energy is used to overcome the what you call external work is done to pushing back the surrounding atmosphere. So more energy required. Okay. So we learn up to here. Okay, we need to strengthen this idea again. So the quite common formula they'll ask about specific capacity and latent heat is just now, like question just now. Body A, body B, okay, at a different temperature, maybe theta 1, theta 2, they are given their own specific capacity and their own mass. And they tell, when they both combine, they'll ask A plus B together, they'll ask, what is the final temperature? This is the common question they'll ask. Okay. So let's say theta 1 is 70 degrees Celsius, theta 2 is 30 degrees Celsius. Okay. So final temperature you're looking for. The C1, let's say 1000 joule per kg per Kelvin. C2, let's say is 2000 joule per kg per Kelvin. Mass, let's say this is 1 kilogram, this is 2 kilogram. Okay. So when these two mix, what is the final temperature will be attained? So how do you calculate this? Final temperature. 70, 30, 1000, 2000, 1 kilogram, 2 kilogram. What is the final temperature attained? So energy, who lost energy? Who lost energy?
A.
So energy lost by A should be equals to energy gained by B. So always you write MC theta, the temperature change. Yeah, temperature change. Remember this is important. The one you need to put earlier is the always the big temperature. The big temperature, put it earlier. So for A of course the temperature 70 dropped to final temperature. So you write here theta minus 70 minus theta or theta minus 70. So you write 70 minus final temperature. Okay, always big minus small. Okay, for the B, so MC of B, temperature, how do you write? Temperature B from 30 degrees Celsius, you go to theta F. So how do you write? Big minus small. So which is big? Theta F should be big than 30, right? Because 70, 30, I think the final temperature must be between 70 and 30. So here you suppose to write what? Theta F minus 30. Okay, so this is what you need to know. So whenever two body are thermal equilibrium, thermally contact, and final temperature attached, the first thing you must write is some lost energy, some gain energy. The one high temperature lost energy, the one low temperature gain energy. Then you write MC theta, and you write the temperature, final big temperature minus small temperature. Don't put final minus initial. Big minus small. You want to be positive. Big minus small. So use your common sense lah, which is big, which is small. Okay. Yeah. So this is how you have to do. Sometimes during this, let's say final temperature for this case, let's say final temperature, let's say I say final temperature you got, let's say 40 degrees Celsius. Okay, 40 degrees Celsius. Let's say the A as a melting point, the A is a solid, let's say as a melting point, not to say melting point, it's in terms, let's say A is in form of liquid, liquid. The freezing point, let's say the freezing point happens at 40 degrees Celsius. Sorry, 35 degrees Celsius, let's say. Oh, sorry, made a mistake. 50 degrees Celsius. Okay, 50 degrees Celsius. The final temperature is 40 degrees Celsius. So how do you adjust the equation here? So A not only MC theta, so you need to be add with what? M, L, freezing, yeah, so fusion, MLF to be added. Okay, MLF plus MC 70 minus theta F must be MC theta F minus 30. So sometimes melting, the freezing can happen. Okay, latent heat of fusion might appear in the equation. So you have to check the melting point and boiling point of both. Okay. So any questions from here? Okay, this is a common question. When A plus with B, what is the final temperature? So when final temperature, energy loss equals to energy gain. In energy loss, don't think always MC theta can be added with latent heat. Depend to check the freezing point and boiling point of that substance. Okay. Okay, so any question of this? No question, Okay, so we're going to do one question about this kind of question. When two added, what is the final temperature? Okay, so let me. So this is the Passia. Okay, the Passia of temperature thermal. I'm going to show you one question. When two bodies are thermal contact, find the final temperature. Yeah, this one. Okay, this is the June 07, question 2. Okay, we go straight to part C. Yes, 2 minutes for you. Use the concept I teach you just now. Get the answer. Okay, 2 minutes for you. Energy lost equals to energy gain. Energy loss could be MC theta, could be latent heat also sometimes. You have to check. Give me the final answer. So ice, they pour some water here. They pour some water. The water was found to be originally under 60 gram. Maybe this you consider as a body A, water. Water, okay. And it was 100 degrees Celsius. Body A is like 100 degrees Celsius. The water has a specific capacity of 4.2 kilojoule per kilogram per kg. Kelvin. Some of the ice melts and final mass of the water is 365 kilogram. Oh, then the ice melts, some ice melts, so causes the total mass become 365 gram. So how much of ice has been melted? 365 minus 160 lah. The ice which is melted. Melted how much is 205 lah. 205 gram of ice has been melted. Okay. So assuming no heat gain from the atmosphere, so there is no, assume no energy has been absorbed from the atmosphere. Calculate the value in kilojoule per kilogram for the specific lethargy rate of fusion of ice. So they're asking LF for the ice. Is how much? So how do you do this? How do you do this? So energy lost equals to energy gain. Okay. Who lost energy here? Who lost energy here?
Water.
The water, right? The water lost energy. Because water is high temperature, 100 degrees Celsius. Lost energy. And the energy gain is the ice. Okay. So what is the loss of energy of the water? What is the loss of energy of the water? Is it water change phase? Water change phase or not? Anyone?
No.
Oh, hot water on ice, So is it the water change phase? Look like you see here, doesn't change phase, right? So energy loss in water, use what formula? What formula do you use?
E equals to
You use
MC.
ml. So just MC theta. Just MC theta. Okay. MC theta. Okay. So M how much? M of water. M of water is 0.16 kilogram. C is what? C of the specific capacity of the water. 4,200 joule lah. And okay, how much theta you write? What is the temperature change of the water? Water original temperature is 100 degrees Celsius. What is the final temperature of this system?
100 minus.
Anyone? What is the final temperature of this system? Original is 100. The water was 100. The ice is 0. But ice is very big, It's a huge ice. It's a very big ice. So final temperature going to be how much? So final after thermal equilibrium achieved, when water is already melted to 365, thermal equilibrium is already achieved. That means final temperature is still what?
0.
Because ice still left, still got ice. So that means the temperature should be
0.
0 degrees Celsius. Final temperature is 0 degrees Celsius. Like in Antarctic, you pour a little hot water on the ice, the hot water temperature will drop from 100 to 0. So the ice will melt. But finally, when thermal equilibrium achieved, okay, so all will end up in 0 degrees Celsius. Okay, 0 degrees Celsius. So what is the temperature change for the water here?
100 Kelvin.
So it's 100, right? 100 is 0. 100 minus 0. This is the energy released by the water. Okay. What is the energy gained by the ice? MC theta or MLF? Is it latent heat or MC theta? Ice. Is it temperature for the ice change? Till 0 degrees Celsius, right? Final also 0 degrees Celsius. So the ice only melted. So what formula do you use? The energy gained by the ice. So just MLF. This MLF. The latent heat of fusion of the ice is gained by the MC theta. But what mass do you use? What is the mass for the ice you use, which is melted? How much of mass melted? Anyone? How much of ice has been melted? 200?
5 gram.
205. So the ice melted is 0.205. Okay, and multiply by the LF. That's it. So find the LF. Okay. So anyone got the answer?
Wait. Teacher, why did teacher change the value of 160 gram to 0.16?
Oh, 0.16, because I changed to kilogram.
Because 4.20 is for kilogram.
Yeah. So mass also have to be kilogram. No?
But 42000 is for gram, right?
No. This is kilojoule per kilogram, right?
Yes.
I got 4,200 joule per kilogram. So the final answer I'll get in joule, but they want in kilojoule. If they want in kilojoule, if they want kilojoule, you just can leave it as 4.2. Can leave it as 4.2. So see, you take it as 4.2, but mass must convert to kilogram. 0.16 kilogram. Okay?
Okay.
Because the latent heat is in kilogram. So anyone got the answer?
$328K.
328 K kilojoule per kg. 328 kilojoule per kg. Okay, so this is an example of body A thermal contact with body B. So energy loss equals to energy gain. But energy lost here is the water, MC theta involved. But something new, energy gain of ice is purely latent heat, MLF, because it's only melted. So MLF, MCF is M latent heat of fusion. So you find the LF, so you get the answer. So, or you confuse whether to have latent heat or heat capacity, draw the graph. Water, for the case of water, the water just dropped from 100 to 0, okay, 0 degrees Celsius. So when the line goes down, it's MC theta. Okay. For the ice, I think I think at 0 degrees Celsius, it's just flat. Line is flat. Okay, it just melted. So therefore, it's MLF. Okay. Any questions from this example? Okay, you got idea. This very frequent, they'll ask like this: A contact with B. What is the final temperature? Question like this. Okay, not always MC theta equals to MC theta. That's what I'm trying to emphasize here. Okay, sometimes latent heat can involve. Okay. So if you don't have question, we can go to the another one. No questions, eh? Hope you understand. We'll go to the next one, eh?
Apa tu? Oh. Oh.
Okay, next one, pretty challenging one. If you can do this, you already mastered this kind of questions. Okay, part B. This one. This is Juno 3, question 2B. Eh? Or you can go for page 3. Okay, part B. Okay, 2 minutes for you. Read the question, check which is energy loss, which is energy gain. Check, is there any heat, specific heat, latent heat involved? Yeah. 2 minutes for you. Okay, I give you 2 minutes. Try to get the idea. Gold is mixed with silver. A jeweler want to add the pure gold to a silver. The silver is only 5%. So therefore the gold should be 95%. The jeweler melts some pure gold and then adds the correct weight of silver. Okay, correct this. Melt some gold already, and adds the correct weight of silver. The initial temperature of the silver is 27 degrees Celsius. So silver initial temperature is 27 degrees Celsius. Okay. So use the data below, calculate the initial temperature of the pure gold so that the final mixture at the melting point of pure gold. They're asking what? What is the gold? The initial temperature, how much? So the gold and what? The gold and the silver, both of them has been added. Okay, both has been added. Both has been added. And what is the final temperature they attain? Final temperature is what? Calculate initial temperature of the pure gold so that the final mixture is at the melting point of the gold. Okay, so what is the melting point of the gold? In this list, melting point of the gold is 1340. Yes. So they're asking initial temperature, final temperature is 1340 Kelvin. Silver is 27 degrees Celsius. You have to convert to Kelvin. So plus 273.15. So it's 300.15 Kelvin. Okay, so gold is the body A, silver is like the body B. Both are thermally contact. Final temperature becomes 1340 Kelvin. What is the initial temperature of the gold must be? So your working is energy lost equals to energy gain. Who lost here? Who lost energy here? Gold or silver? Yes, guys. Who lost energy here? According to the question. Who losing the energy?
Gold.
Gold lose energy. So the energy loss is gold, and the energy gain is the silver. Okay, so this is easy to figure out. Okay, now you have to check: is there latent heat involved? Is that only MC theta involved? That's the thing. Gold temperature theta. How the gold graph looks like? Gold temperature graph looks like. The temperature versus the time. Initial temperature is theta F. We are looking for. The temperature drops. Finally, it dropped to where? Drop to the melting point of the gold. It becomes 1340. So gold haven't melted yet. You just reached the melting point of gold. That's it. It haven't freeze yet. Okay. So the graph for gold is a straight line. So gold use, is there any latent heat involved for the gold? The temperature of high temperature, you just drop to the melting point of the gold. That's it. It never freeze yet. So the gold involves what? Only MC theta. Okay. MC theta. Okay. Now, theta how much? Theta, how do you write here? Anyone? Theta, how do you write? Final big temperature minus small temperature. Who's the big temperature here? Theta F or 1340? Theta F, right?
F.
Final temperature. Theta F minus 1340. A C specific capacity for the gold given here. 628. But unfortunately, they give kilojoule. So we change to joule now. Can we change to joule? Because latent at the final answer, do they say they want Kelvin? They want final temperature. So all kilojoule, better change to joule. Okay. C change to joule. So C is what? C is your 628 times 10 to the power of 3. Okay, now problem is mass. What's your mass going to be? Is it mass given? Gold, how many percent in the combination? Silver is 5%. So gold, how many percent? It's 95%, right? So how much of mass you write here? Just write 0.95 m. 0.95 m. The final mass is m. Final mass is m. So gold is 0.95 m plus the silver is 0.05 m. This is 95%. This is 5%. Okay, so mass you must put as 0.95 m, or you can put 95 if you want. You can put 95. The other one you can put 5. Also can. Okay. So I put 0.95 m. 0.95. No need to put m also can. You don't want to put m also can. 0.95. Okay. is equivalent to, so gold only MC theta, equivalent to energy gained by silver. Silver, can you draw the graph for silver, the temperature change? How the silver change its temperature? How the graph of temperature graph for silver looks like? I draw here at the bottom. How the silver graph looks like? I draw here. Silver initially what temperature? Initially was 300.15 Kelvin. So it goes up to the final temp. It goes up to which temperature? 1340, right? 1340. So that is a trap here. So gain in silver, is it only MC theta? Is there any phase change during this process? Do silver melted during this process? When you go from 300 Kelvin to 1340, is it experience any change phase? How to know?
It didn't
Check.
reach.
Is there a change phase or not? How to know? Check the melting point of silver. What is melting point of silver? Melting point of silver is 1240.
Oh, yes, reach.
But the final temperature. So what happened to the silver in a halfway of rising the temperature? Halfway it was melted.
Yes.
So 300. So how the temperature versus time graph looks like for silver? It goes up, then up to which temperature? 1240. It was flat, melted. Then the temperature rise again up to what temperature? Up to 1340. And this is what happened for silver. This is the graph for silver. Okay. So energy gain by silver. What formula do you use here? Do you use MC theta or do you use ML or do you use both? So both need to be used. So both. So for silver should be MC theta plus MLF. Okay. It should be MLF. So now M, how much use? How many percent of silver? So it's 5%, so I put 0.05. C, what is the C of silver? Specific capacity, 105. So I put 105 times 10 power of 3. Temperature change, how do you write? How much temperature change for silver? Silver, what is the temperature change? From 300, so here you got one MC theta. Up here you got another MC theta. Okay. But these two MC theta can be added. So the temperature change is what? 1340 minus with 300.15. You can merge them. Both lines, straight line, you can merge them. So 1340 minus 300.15. That's your. Yeah. Any questions?
For both your C, you wrote latent heat instead of specific heat capacity.
Oh yeah, sorry. Specific capacity is 129.
Oh yes.
Oh sorry. So both must be 129. For the gold here 129. So here C is what? 235. Sorry, it's 235. Okay. Then finally plus with M again for the silver is 0.05 times LF. LF is the length of fusion for the silver. And now 105. 105. So you put 105 times 10 power of 3. Okay, so this is the equation you're supposed to write. Then you rearrange, you can find the final temperature. Okay, so this is a tricky question. Body A connect with body B thermally, but what happened? The mass they give in terms of percentage. So you should know how to write. If they give in percentage, you can write like a fractional format. 5% you can write 0.05. 95% you can write 0.95. Okay. Another one problem here is the melting has been done between the temperature rise. Melting is experienced by the silver. It's very hidden. If those who have never watched the melting point of the silver is 1240, they only will put MC theta here. They forgot to put MLF because they never see there is a melting happen, because you need to be alert. The final temperature was 1340, but the melting point of silver is lower than 1340, so melting should happen. So MLF appeared here. So MC theta of the gold equals to MC theta plus MLF of the silver. Okay, so best is when you read this question, you try to draw the graph. You try to draw the graph. Then I feel that you won't miss out the melting point, the melting process. So here, if you draw the graph, you can you get this MC theta plus MLF. Okay, another one problem given in here is the kilojoule change to joule. Another problem they give is degree Celsius must change to Kelvin. So a lot of conversion involved. Okay. So anyone got the final answer? How much? What is the original temperature? This is not a final temperature. It's original temperature, initial temperature.
1480.
1480. So 1480 Kelvin. Okay. So let's see 203. Yeah, so this is the working. Okay, this is the working. Supposed to get. Okay. So heat lost by the gold is MC theta. Heat gained by the silver is MC theta plus ML. Then you find the final temperature. 143. The final temperature is 1483. Okay. Okay. Any questions, guys, from here? So very common. A plus with B. What is the final temperature? So not always MC theta equals to MC theta. Can have ML beside. So check the melting point, boiling point of them. Okay, is it melted or boiled? Check that. Draw the graph, my advice. Temperature versus time. Temperature versus time for both of them. So if it's a flat line observed, then ML is involved. Okay. Okay, so last one. Okay. Okay, question November 2. No, don't need to do this. Sorry. Yeah, let's retry this. November 2. Latitude of specific capacity and latitude of vaporization. Use the concept.
Everybody wants to drink. Everybody can.
Okay, 2 minutes for you.
Yeah. Y'all feel great, man. I feel good, baby. I feel great, man. I see no on the test.
Okay, I hope everyone give me the answer for this. 2 minutes for you.
Everybody 1, 2, 3. Everybody.
Kettle rated 2.3 kilowatts. A mass of 750 grams of water at 20 degrees Celsius is poured into the kettle. When the kettle is switched on, it takes 2 minutes for the water to start boiling. In a further 7 minutes, 1/2 of the water is boiled, or 2 minutes for the water to start boiling. 7 minutes, half of the water boil. Okay. Estimate for this water the specific heat capacity of the water. So what's formula? So the energy equals to MC theta. How do you calculate the energy? Energy must put PT, right? Power times the time. Power how much? Power is 2300 watts. Time. What is the time you're going to put here? Anyone? Time for it to rise the temperature. What is the time taken for it to go to the boiling point? Anyone?
120 seconds.
So it's 120 seconds, just 2 minutes. Mass, the entire water has been raised to that temperature, so it should be 0.75 changed to kilogram. And C is the one we are looking for. Temperature change is how much? 100 minus 20. Okay, those who are calculating, hope this is how your calculation should be. Which later gives you the C. So anyone, what's the answer? So conversion, kilowatt change to watts, time, minute change to second, mass change to kilogram. So a lot of conversion, physics. Every question there will be a conversion, so be careful. So C, what's the answer you got? Anyone? Joule per kg. 4602. 4602. Okay, 4602.
4,600 only, sir.
4,600. Okay, good. So this is a little okay, fine. We go to the next one. Find the specific Lethonid of vaporization. Okay, 2 minutes for you. Okay, so you have an idea how to find Lethonid of vaporization. So the energy absorbed should be equal to MLF. So how much of energy has been absorbed during this melting? Again, PT to be used. PT, MLF. Okay, let me scroll down. What power do you use? The same power lah. The power you use how much? The same heater, right? So it's 2,300. Time you use how much? How much? What is the duration it was melted? 7 minutes. So the time should be 7 minutes. So change to seconds. So 7 times 60 goes to The trap is the mass. Okay. At 7 minutes, how much of mass of water has been boiled? Only half of the mass of the water is boiled. So the energy for 7 minutes here is used to melt how much of mass? Half of the 0.75. So this should be 0.75 divided by 2 is the mass to be used. Okay, that's the trap. Okay, half of the mass of the water is boiled. Okay, those who have discovered this, I think then you can find the answer. So you can get there after that.
Okay, what time is balik? You balik 1 o'clock. Oh, makan.
Okay, class, so you get the answer? Anyone?
Okay, the food, Okay, I cannot get it from my I want to ask one thing. Is there any word?
2576 kilojoule kg minus 1
1,576,
kilojoule.
76. So we go for 80 lah, 2,580 kilojoule. Because we don't write for SF, so not more than 3. So 3 SF is fine. Kilojoule per kilogram.
Yeah.
But they want joule. So joule then is going to get even bigger. Here we put all in standard 2,300. 2,300 is in joule. Oh, it's already in joule, right? This is already in joule. So final answer in joule, right? No. Do you put 2,300 or 2.3? Your calculation.
2300.
2,300. So final answer is in kilojoule or joule?
It was in joule, but I make it.
Oh, you changed it.
Yeah.
Okay. So okay, November 2, Yeah, so you get 2.6 times 10 power of 6 joule per kg. Q equals to ml, so half of the mass to be used. Get the answer. Okay. So yeah. So finally, they're asking. That's the question. Take one assumption made in your calculation and explain whether there will lead to overestimate or underestimate of the value of the specific latent heat. What is the one assumption you made? No energy loss to the surrounding. No energy loss to the surrounding. Okay. Explain whether it will lead to overestimation or underestimation of the value of specific latent heat. Anyone?
Overestimation.
Overestimation. The PT higher than supposed to be because some energy lost also we counted here. So overestimation. So we assume no energy loss to the surrounding. This will lead to overestimation of the latent heat of fusion. Okay. Okay, students. So yeah, we just halfway of this topic. Okay. So far we did what? So far we're done with the specific capacity, latent heat of fusion. Okay. So the next class we will go in something new which you never learned before, internal energy and first law. Okay, this might take 2 classes. Okay, to finish off this. Okay, any questions, guys? Today's lesson. I think majority is like just a revision of your whole studies. not something new. Something new, I see the question is harder. Okay, so I stop here. So see you on Monday. Okay. Any questions? No questions, huh? Okay, guys, stop.